Okay, so today we're going to talk about something new called empirical and molecular formulas. So first I'm going to define what those are, and then I'm going to do an example here. And then on the back of your worksheet, we're going to do an example down here for these kind without the pictures, okay? So first I'm going to start with the definitions. So the empirical formula is the lowest whole number ratio of elements in a compound. Okay, and then we're going to add in parentheses that it cannot be reduced. Okay, so an empirical formula is the lowest whole number ratio of elements in a compound and can't be reduced. The molecular formula is the actual ratio of elements in a compound and then I'm going to add in parentheses that it can be reduced. Okay, so we have the lowest whole number ratio for the empirical formula and the actual ratio for the molecular formula. Okay, so let's look at this example here. We have a picture of a molecule. This is the actual structure of ethanoic acid. And I first want to know the molecular formula. So that's going to be the actual formula that you count from the picture. And it gives you a hint here. It says write the symbols alphabetically. Okay, so alphabetically we would go C, then H, then O. So we're literally going to write down how many of each element there are, and that's going to make our formula. So we have two C's, so that's going to be C2. And then we have 4 H's. So H4. And then there are 2 O's, so O2. So again, it's in alphabetical order. C comes first. There were 2 of them. H is next. 4 H's. And then 2 O's. And that's how you write the molecular formula. So if you'll notice, this is the actual ratio because I could reduce a 2, a 4, and a 2. Think about when we're writing formulas and we crisscross and I say, can we reduce that? Yes, we could reduce this. And that's what's going to make our empirical formula. Okay? But the molecular formula could be reduced, can be reduced. It's the actual ratio. The ratio is 2 to 4 to 2. Okay? Now it says, what is the biggest number that you can divide each subscript by? Okay? So if I tried to divide each of these by 1, I could do it, and then nothing would change. But that's not the biggest number I could divide them by. The next number up would be 2. If I divided all of these by 2, I'll use a different color. If I divided this by 2, and this by 2, and this by 2, okay, I would end up with 2 divided by 2 is 1, so that would be C. We don't write ones in formulas. 4 divided by 2 is 2, so H2. And then 2 divided by 2 again is 1. So this is our empirical formula. I cannot reduce a 1, a 2, and a 1, that ratio, any further, okay? And the biggest number I can divide each subscript by happens to be 2. Sometimes it'll be a 3, sometimes it'll be a 4, but you need to go as high as you can in order to get something that is not reducible, okay? The reason why I can't reduce a 1, a 2, and a 1 is because if I divide those, I would end up with fractions, and we can't have fractions in formulas. Sorry, I hit my phone. Okay, so again, molecular formula is the actual formula when you count them up, and you're going to write them in order alphabetically. To figure out your empirical formula, you're going to figure out the highest number you could divide each subscript by, and then do that, and that should be your empirical formula. Remember, your empirical formula cannot be reduced. I no longer can reduce this. So it has to be the exact same number you divide by on each subscript. So it's not like you can divide one of them by 2 and the other one by 3 or something. It has to be the same number for each subscript that you divide by in order to find the empirical formula. Okay, so that's what you're doing on all the ones with the pictures. Don't worry about double bonds or any of that stuff. You're literally just counting. Sometimes it helps if you highlight or circle the ones that you've already counted, because Like, look at this example over here. Sucrose looks kind of crazy, so you're going to have to go a little bit slow. It's not all going to be as simple as this, okay? So now I'm going to show you how to do it when you don't have a picture. So I'm going to do an example down here in this area. Okay, so I'm going to do it exactly in order, like the A, B, C that you see here. So first, we're going to start with an empirical formula. So I'm going to give you an empirical formula. Okay, so I'm going to say that the empirical formula is C3H4O. That's our empirical formula. The reason why we know this is empirical is because it cannot be reduced. A 3, a 4, and a 1 do not have enough in common. Okay, cannot be reduced by the same number. All right, so the first thing you're going to do in part A of each of these is you're going to find the molar mass. So molar mass is still there. It's not going away. Okay, so if you remember, molar mass is when we make our list. So I have C, H, and O. My number of C's in my formula is 3. My number of H's is 4, and my number of O's is 1. And then I'm going to multiply those by their mass from the periodic table. Okay, so if you look up carbon, the mass is 12.011. Hydrogen, it's all the way to the left, is 1.008. And then hopefully by now you know oxygen is 15.999. Okay, some reminders. You're going to type in 3 times 12.011 plus 4 times 1.008. And then plus 1 times 15.999. So I'm going to go ahead and do that now. 3 times 12.011 plus 4 times 1.008 plus 1 times 15.999. Okay, so what I got is 56.064. And remember, molar mass is measured in grams per mole. Okay, so that's our answer for part A. Okay, so part B is going to give you a molecular mass. So I'm going to say if the molecular molar mass is 168.192 grams per mole, how many times greater is the molecular formula? Okay, so if the molecular molar mass is 168.192 grams per mole, how many times greater is the molecular formula? So the way that you're going to find that in part B of these is you're going to take your molecular molar mass and you're going to divide it by your empirical molar mass. Okay, so your molecular molar mass will be given to you. Okay, and that's what they gave me in this part B right here. It gave me a number. That's our molecular molar mass. Our empirical is what we just calculated in part A. So I'm going to go ahead and write that down. So it's going to be 168.192 divided by the mass we just solved for in part A, which is 56.064. All right, so I'm going to go ahead and divide those. 168.192 divided by 56.064. Okay, and I got exactly 3. Okay, so how many times greater is it? It's 3 times greater. Okay, and then for part C, it says, what is the molecular formula? So we're going to write the molecular formula. Okay, so what you're going to do for this part is you're going to take this number from part B, however many times bigger it was, and that is your multiplier. That's what you're going to multiply every subscript in your empirical formula by to find your molecular formula. So what these last questions are showing you basically is how to go backwards. Okay, the beginning is starting with your molecular and reducing it so you get your empirical, dividing by a subscript to find your empirical. This is literally starting with the empirical, figuring out your multiplier, and then finding the molecular. So it's like the backwards way, okay? But both are equally important. So you're going to take your multiplier here. That means I'm going to take each of these subscripts in my original empirical formula, and I'm going to multiply each of them by 3. Okay, so that is going to be C and then 3 times 3, and then H and then 4 times 3, and then O 1 times 3. Okay, but I'm going to rewrite it as a formula. Okay, so what is 3 times 3? Good, it's 9. And then what is 4 times 3? So that's going to be H12. And then what is 1 times 3? O3. So my molecular formula, my actual ratio, is C9H12O3. Okay, notice this could be reduced. If I divided all of these by 3, I would end up with my empirical formula. I just showed you a way to kind of go backwards. Okay, remember, you can always email me or contact me on Google Voice if you have questions.